Hello everyone, myself Rajyalakshmi. So for this semester I am going to deal you pharmaceutical organic chemistry. So today we will discuss unit 1, that is benzene and its derivatives. Okay, so coming to the introduction. So first of all, before going to introduction of benzene, so a small brief discussion about hydrocarbons. Okay, so first of all, what are organic compounds? So in chemistry, organic compound means generally they contain carbon and hydrogen in their structure. So, so from those compounds, so more number of compounds will be derived. Okay. So coming to the classification of hydrocarbons, there are two types of hydrocarbons: aliphatic hydrocarbons and aromatic hydrocarbons. So aliphatic means they contain straight structure. Okay. So there is no cyclic structure. So which include alkenes. It is methane, ethane, propane, that is methylene or ethylene in case of alkenes. Okay. Next, aromatic hydrocarbons. These contain one or more benzene ring in their structures, so they are also called aryls. So an aromatic hydrocarbon group is called an aryl. Aryl means so benzene ring which is attached to a substance of alkyl group, that is R, aralkyl. It is called as aralkyl. So aryl means benzene. Uh, in benzene ring, one of the hydrogen is substituted with other groups. Okay, that is aryl. So if the benzene ring, so the carbon is attached to the alkyl group. It is called as aralkyl group. Okay. So next one. So coming to the introduction of the benzene. So before going to the introduction, first of all, what are coming to the definition? uh, Aromatic compounds. So first, the term aromatic compounds derived from the August Kekulé. First, August Kekulé in 1865 he used the term aromatic compounds. Okay, so then uh, why? Because they had fragrant odor or aroma. Okay, so this is the main distinguished property from the aliphatic hydrocarbons, where they had lacked the odor, lacks odor. So aromatic compounds does not contain, sorry, aliphatic hydrocarbons does not contain any odor like aromatic compounds. Okay, coming to the discovery of benzene. So the word benzene derives historically from gum benzoin. Michael Faraday in 1825 isolated benzene from the oily residue derived from the production of illuminating gas. Okay, giving it the name bicarbonate of hydrogen. First of all, he isolated benzene from the source of production of illuminating gas. Okay, then in 1865, August Kekulé derived the structure of benzene. So before he deriving the structure in 1834, in 1834, Ilhad Micher, Ilhad Micheris, Ilhad Micheris synthesized the benzene, synthesized the benzene. Okay, afterwards, August Kekulé derived the structure of the benzene. Okay, next coming to physical properties. So this is the small introduction of the benzene. Next, physical properties. So before going to discuss physical properties, the main source of benzene is coal. So the coal is obtained from the trees. Long trees are buried under its crust. Okay, so main source is coal. So physical properties: benzene is a colorless or all light yellow. It is liquid at room temperature and it has a sweet odor. Why? Because it is an aromatic compound. So other natural sources of benzene include volcanoes and forest fires. Okay, so it is also natural part of crude oil, gasoline, and cigarette smoke. So because all those contain carbon. Okay, so IUPAC name of the benzene: 1-cyclohexane or 1,3,5-cyclohexatriene, because it has three double bonds. So this is the main structure of benzene. See ball and stick model. So all white balls are indicated hydrogens, and all black balls are indicated carbons. Okay, this is the space filling model of the benzene structure. So benzene is an organic chemical compound consisting of carbon and hydrogen atoms with alternating double bonds. As it contains only carbon and hydrogen atoms, benzene is classified as a hydrocarbon. Hydrocarbon means they contain hydrogen and carbons in their structure. So main chemical formula of the benzene is C6H6, which is derived by aldehyde. So it consists of 6 carbon and 6 hydrogens. The ratio of the carbon and hydrogen is 1:1. So all are joined in a ring with one hydrogen atom attached to each. So coming to the nomenclature, monosubstituted alkyl benzenes are named as derivatives of benzene. For example, ethyl benzene. So only one substitution is there on the benzene ring. Ethyl benzene toluene. Benzene with CH3 group is known as toluene. This is the styrene. So the IUPAC system retains certain common names for several of the simpler monosubstituted alkyl benzenes. So this is a single substitution benzene we call it as monosubstituted alkyl benzenes. So common names. So these are the some common names for some monosubstituted benzenes. This is the phenol, benzene with OH group, phenol, OCH3 group, anisole, methoxybenzene, also called as methoxybenzene. This is the hydroxybenzene, methoxybenzene, IUPAC name, common name anisole, aniline, aniline, aminobenzene or benzamine, benzaldehyde, C double bond OH, benzene with C double bond OH, benzoic acid, benzene with COOH. Phenyl groups. Phenyl group means one hydrogen is lost from the benzene ring. So the hydrogen is replaced with some other group if substituent is there. Okay, phenyl. This is the 1-phenyl cyclohexene. 1-phenyl cyclohexene. This is the first position. 4-phenyl. 1, 2, 3, 4. 4 C6H5 means phenyl group. 1 at first and second carbon there is a double bond, means alkene. Total number of carbon 4. So 1 phenyl, 1 butane. 1 phenyl, 1 butane. So when two substances are there in benzene ring. Okay, so numbering the atoms of the ring or using the locators like ortho, para, meta. So based on the position. Here it is called as 2-bromobenzoic acid or orthobromobenzoic acid. This is the ortho position, meta position and para position. So the detailed information about ortho, para and meta position orientation is discussed in further classes. We'll discuss in further classes. So this is the bromine substituent. So 2-bromobenzoic acid. 2-bromobenzoic acid. Here, 1 comma 3 dimethyl benzene or methoxylene, because at third position methyl group is there. This is also called as meta position. 1,3 dimethyl benzene. Next, 1-chloro-4-ethyl benzene. Thus, chlorine has give the first priority. That is why we will start numbering from chlorine. Here, from here. 1, 2, 3, 4. 1-chloro-4-phenyl. Sorry, 1-chloro-4-ethyl. CH2CH3 ethyl benzene, are also called as this para position. Para-chloro-ethyl benzene. So up to this, we'll finish our nomenclature part of the benzene. So how we give the name for monosubstituted benzenes, and how we use the names in case of disubstituted benzenes, IUPAC names and common names. Okay. Next, so evidences for the derivation of structure of benzene. So one is based on molecular formula. That means uh, how the molecular formula is derived. Okay, and open chain structure not accepted, and evidences in favor of ring structure. So in that uh, three concepts are there: catalytic hydrogenation of benzene yields cyclohexane. Next, benzene yields one monosubstitution product, and also benzene forms three di and tri substituted product, which can be explained on basis of ring structure. Next, resonance hybrid structure. So finally, molecular orbital structure. So based on these evidences, we will derive the structure of the benzene. Okay. Let us discuss one by one. So first of all, molecular formula. So benzene has a molecular formula C6H6. So from its elemental composition and molecular weight determination, okay, so of benzene known to contain 6 carbons and 6 hydrogen atoms. So, so finally it has a molecular formula of C6H6 as compared to hexane, where hexane contains C6H12, number of hydrogen atoms 12. So which confirms that benzene is highly unsaturated than the cyclohexane. So from this, it was concluded that 6 carbon atoms in the benzene were linked by double or triple bonds, so as to form a straight chain or closed ring as proposed by Kekule. See, you observe the Kekule structures. So this is the ball and stick model of the benzene ring. See, carbons contain double bonds. So this is the Kekule structure showing all atoms, means carbon, hydrogens, carbon, hydrogens. This is the cyclic form of the Kekule structure, cyclic form of the. So Kekule structure as a line angle formula. So it contain alternate double bonds. So second one is open chain structure not accepted. So because it looks like a alkanes, aliphatic type of structure. Okay, structure 1, structure 2, structure 3. So all these structures were ruled out because benzene did not give the usual reactions of alkenes and alkenes. Why? Because here alkenes and alkynes undergo addition reactions where uh, aromatic compound does not. So due to the loss of aromaticity, they did not undergo addition reactions. So that is where the possible open chain structure of benzene, uh, the possible open chain structure is not sorry, the possible, so that is why the straight chain structure is not possible. Okay, 1 2 3 4 5 6 carbons, 6 carbons. This structure one contains alternate double bond, single bond and triple bond. Okay, this alternate triple bonds contain triple bonds and single bond. So all these type of structures undergo addition reactions. So which is the typical characteristic property of alkanes and alkynes. So for example, when above open chain structured compounds containing double and triple bonds are added to a solution of bromine and carbon tetrafluoride, so which is red in color, become colorless. Red color become colorless. But benzene do not gives these reactions because benzene cannot have open chain structure. Okay, so why this? Actually, this is the addition reaction. Addition reaction occur here. So double and triple bonds are added to solution of bromine because the bromine will go and add to uh, the, the open chain structure. Okay, so where there is no possibility in case of benzene because it has because benzene cannot have open chain structure. It is in the form of cyclic structure. So that is why addition reactions are not possible in case of benzene. Okay, and another reason is due to loss of its aromaticity. When uh, addition reaction occur on the benzene, it loses its aromaticity. So it is also one of the criteria. Okay, so evidence in favor of ring structure. In that, first one is catalytic hydrogenation of benzenyl cyclohexane. It also called as hydrogenation reaction. So these three hydrogens will go and add to these three double bonds. Unsaturated compounds become saturated compound here in the presence of platinum or nickel catalyst. That is why we call it as catalytic hydrogenation. Okay, upon heating we get the cyclohexane. Okay, since hydrogenation is not bringing about any major structural change in carbon frame, so it proves the presence of closed ring of 6 carbon atoms in benzene molecules. Okay, does not change any carbon frame. So it saturates the double bonds. Okay, see here. So benzene with acids does not give any reaction. In bromine solution also doesn't give any reaction. With potassium permanganate also does not give any reaction. Okay, so it has aromatic compound. So here you see alkenes, cyclic alkenes. These are the cyclic alkenes. So this will undergo addition reactions. Okay, because these are not aromatic compounds. See, with acid go and add OCH3, OSO3H, bromine. Two bromine atoms go and add to on the cyclohexene ring. Here with potassium permanganate undergo oxidation reaction. Okay, cleave the ring, and add carboxylic acid groups. Oxidation. Okay. Here general, this is the general reaction for the alkenes. See, this is for example alkene. This is the electrophile. Assume this is the electrophile. So attacking of the electrophile. So in third step, in second step, carbocation intermediate is formed. So the electrophile will go and attack at the one carbon, cleave the double bond and add on the carbon. Next, nucleophile attack. Assume it is as a nucleophile. So another carbon will add in the nucleophile. So finally, addition product will be formed. Product of electrophilic addition product. Okay. See what will happen if benzene undergo addition reaction and what will happen if benzene ring undergo a substitution reaction. Okay, which is suitable for it. Okay, so for that you take benzene and then electrophile, add the electrophile, so to form carbocation intermediate for addition and substitution. So both for both the reactions, the carbocation intermediate is the complex major intermediate complex. Okay, see here, in case A, in case A, electrophile will proton elimination eliminate the proton and this electrophile is substituted on the carbon. Okay, in case B, in case B, so this nucleophile, sorry, in case A, this nucleophile will abstract the proton from the benzene ring and to form the byproduct HZ, and this is the substitution product. In case B, so the nucleophile will go and attack this on this positive carbocation, positive carbocation carbon. Okay, so here there is a here benzene ring loses its aromaticity. In case A, benzene does not lose any aromaticity and give the electrophilic substitution product. So here it loses its aromaticity. So that is why here the product is not stable. Here the product is stable, more reactive. This is less reactive. So that is why benzene undergo substitution reactions rather than the addition reactions. Okay, this is the addition product. This is the substitution product. So here loses its aromaticity. Here it's retain its aromaticity. This is the major reason. So benzene yields one mono substitution product. So if bromination is done, only one bromobenzene is obtained because one of the hydrogen atom is replaced by the bromine. So it is same in the case of chlorobenzene and nitrobenzene. So chlorination yields one chlorobenzene, nitration is one nitrobenzene. Okay, so this proves that each hydrogen must be exactly equidistant. So all hydrogens are lie in the same plane. So this is comes under molecular orbital picture. So let me explain further slides. So next, equidistance to other hydrogen, since the replacement of any hydrogen gives the same product. So far, if we substitute, if we replace the first carbon also, we'll get the same product. If we replace the first hydrogen also, we'll get the same product. Second hydrogen also get the same product. So why? Because all hydrogens are at equidistance. So that is why bromination of benzene give the only one product, one bromobenzene. Okay. Next one. 。 bromination. So benzene, another means benzene forms 3 di and 3 tri-substituted products. So for this one monosubstitution product, I will share one more PPT. See here, benzene benzene yields one monosubstitution product. So only one bromobenzene is obtained when one hydrogen atom is replaced by bromine, because all hydrogen atoms in benzene are equivalent. In the presence of PBr3 will give the only one monobenzene is possible. Okay. So next, benzene forms 3 di and 3 tri-substituted products, which can be explained on basic of ring structure. See here, 2,6,3,5. Okay, these are the same position. Okay, also called as ortho positions. The product will get it. The product we will get is known as the ortho product. This is the meta position and this is the para position. So position 4 is the para position. Para product, meta product, ortho product. Okay. So depending on the nature of the substance, so the upcoming depending on the nature of the substance, the upcoming electrophile, that means this the nature of this group, the upcoming electrophile will go and attack it, ortho, para or meta. It's totally depending on the this group, the nature of this group, whether it is electron withdrawing or electron releasing. So whatever it may be, based on this nature of the group, the electrophile will go and attack it particular position. It means ortho, para and meta. Bromination, benzene forms 3 di and tri-substituted product, which can be explained on basic of ring structure. See here, 2 and 6 same, so ortho product, 3 and 5 same, meta product. So therefore only 3 dibromobenzene are possible. Okay, ortho, meta and para. Here, here, here. Next, evidence, resonance, hybrid structure. So these are the Kekulé structure, structure 1 and structure 2. So only there is a difference in the position of the electrons, not in the carbon atoms. Okay. So there is a difference only in the position of electrons. Okay, benzene is a hybrid of structure 1 and 2, which are exact equivalent and have same stability, and they make equal contribution to the hybrid structure. Okay, so the resonance stabilization energy, which is responsible for the unusual stability of benzene, so which can be calculated from the measurement of heat of combustion or heat of hydrogenation reactions. So benzene stability, it means heat of hydrogenation reactions are very very important. Okay, so resonance means interaction between the pi bonds, lone pair of electrons and pi bonds. This is called as resonance effect. Okay, Here resonance hybrid means there is a difference in the arrangement of pi bonds, not in atoms. So stability of benzene. Stability of benzene can be explained in the following way. Heat of hydrogenation is the quantity of heat evolved when the mole of an unsaturated compound is hydrogenated. See here, 1 mole of alkene, cyclohexene, that means cyclohexene. So one double bond is hydrogenated here. We get the product cyclohexane and the heat evolved energy is 28.6 kilocalories per mole. Okay. So addition of hydrogen to the double bond is an exothermic reaction. So this type of reaction also called as exothermic reactions. Okay. As heat is given out in the hydrogenation means the product in each case is more stable than the original one. So so this is the less stable product than this. So this is the more stable product than the original one. Okay. Hydrogenation of the single double bond give the product cyclohexane. That means cyclohexane to cyclohexane with the evolution of energy 28.6 kilocalories. Next, hydrogenation of two double bonds. That means cyclohexadiene to form cyclohexane with the evolution of energy 55 kilocalories per mole. Next, benzene or 135 cyclohexatriene. 135 cyclohexatriene. So undergo hydrogenation to form cyclohexane with the evolution of energy 50 kilocalories per mole. Okay, so these are the main important stability reactions of benzene, also called as exothermal reactions. Okay, so this is the hypothetical picture of the stability reactions of the benzene. See here, one double bond hydrogenation, that means cyclohexene, cyclohexadiene, and cyclohexatriene. Okay, total energy 85.2 kilocalories. So this is the 36 from cyclohexatriene to cyclohexane. If for this evolve the energy is 36 kilocalories, that is resonance energy of the benzene. So this is the actual resonance energy of the benzene ring, 36 kilocalories. Okay, so this is the hypothetical picture of benzene, stability of benzene. So in this heats evolved on hydrogenation of 1 mole of cyclic compound. So total energy లో నుంచి 50 kilocalories per mole minus చేస్తే remaining 35.8 kilocalories. This is the resonance energy of the benzene. Right? Cyclohexane has heat of hydrogenation 28.6, whereas cyclohexadiene 55, almost double the energy. So we expect cyclohexadiene to have heat hydrogenation about 3 times. So 20.28.6 into 3. Okay. So as large as cyclohexane, which should be about 85.8 kilocalories per mole. So and the value of benzene is 50 kilocalories per mole. So that means when benzene is actually hydrogenated, only benzene 50 kilocalories per mole of heat is evolved. So difference between the total energy and for the formation of the benzene. Cyclohexene to benzene. Okay, give the energy 35.8 kilocalories per mole. Okay, this is the actual energy of the benzene. Molecular orbital structure. So, by the X-ray diffraction mechanism, it is proved that benzene consists of a planar hexagon of 6 carbon atoms having the carbon-carbon single bonds which are equal in length. The length is 1.4 angstroms and carbon-carbon-carbon bond angles 120 degrees. So therefore it can be proved that each of these 6 carbons in benzene ring is in the state of trigonal hybridization. Is is in the state of trigonal hybridization. So the ring system is constructed from 6 sp2 hybridized carbons. So by the overlapping of the two hybrid orbitals, each to form sigma bonds. Overlapping of the sp2 hybrid orbitals. So the structure of the benzene molecule is best described in terms of modern molecular orbital theory. So according to theory, all the carbon atoms in benzene ring are sp2 hybridized. Okay, so remaining 6 sp2 orbital of 6 carbon atoms overlap with each other and one s orbital of 6 hydrogen atoms overlap with one s orbital of 6 hydrogen atoms individually to form a sigma 6 sigma bonds. So these are the carbon hydrogen sigma bonds. All carbons are sp2 hybridized. Okay, the sp2 hybridized carbons overlap with each other and with the s orbital of the hydrogen. So form carbon-carbon and carbon-hydrogen sigma bond complex. Okay, formation of carbon-carbon and carbon-hydrogen sigma bonds. So and one more thing here. So each carbon also one unhybridized p orbital containing one electron. Okay, so these are perpendicular to the plane. Okay, okay, so which overlap with each other and forming a pi bonds and forming a pi bonds. Okay, so this is the molecular orbital picture of the benzene. So all carbons and hydrogens are lying in the same plane. One half is above the plane and other half is lying the below the plane. Unhybridized p orbitals containing electrons to form the pi bonds. So up to this, these are the various evidences for the derivation of structure of benzene: synthetical, historical, synthetical, and molecular orbital picture of the benzene ring. Okay, so next coming to Huckel's rule and aromaticity. So Huckel's rule refers to the number of electrons, not the number of atoms. Okay, for example, 2, 4, 6 and 2, 6, 10, 14, 18, and so on contain these number of electrons. Okay, and also satisfy the Huckel's rule. So the compounds to be known as the aromatic compounds. So what are the main criteria for the for a compound to be known as aromatic compound and to satisfy the Huckel's rule? Okay, the complete delocalization of the pi electrons caused by side overlapping gives the benzene aromatic character. Okay, so an aromatic compound must contain 4 and plus 2 pi electrons. So here n is equal to positive integer, this is 0 to 9. So what are the main criteria for a compound to be an aromatic? First one is cyclic. Okay, next planar. So all the adjacent p orbitals are aligned in the same way. So and completely conjugated compounds that contain only 4 and 5 electrons, which are especially unstable and are said to be anti-aromatic. So benzene is aromatic and especially stable because it contains 6 electrons. So cyclobutadiene is anti-aromatic and especially unstable because it contains 4 pi electrons. So here this is the anti-aromatic compounds because it satisfies 4 and 5 electrons. Here benzene is the aromatic compound. It satisfies the 4 and plus 2 pi electrons. Here you will get the 6 pi electrons. You will get the 4 pi electrons. 2 into double ones means 2 into 2, 4 electrons. 3 double ones. 3 into 2, 6 electrons. So that is why you can reverse the number of electrons, not the number of atoms. So the aromatic compounds apparently contains alternate double and single bonds in the cyclic structure and also undergo substitution reaction rather than addition reaction. So, so this is the main important characteristic behavior is called as aromatic character or aromaticity. So for the criteria for aromaticity, here some rules are derived by the Hickel. Here according to him, rule 1, an aromatic compound is cyclic and planar, must be cyclic and planar. So each atom in an aromatic ring has a p orbital. So these p orbitals must be parallel for continuous overlapping around the ring. See, and as to satisfy the 4 and plus 2 5 electrons. And conjugated also. In conjugated system. That means conjugation is alternate single bond and double bond. So benzene, it is a cyclic planar compound. It has p orbital on each carbon of the ring involved in a double bond. It has 3 double bonds and it is 5 electrons and 6 pi electrons, which is in accordance with Hickel's rule. 4 and plus 2, 6 electrons. 4 n equals to 6 minus 2, n equal to 4 by 4, that means 1. We get the n positive integer. So that compound to be known as the aromatic compound. Benzene is known as the aromatic compound. The number of pi electrons. It satisfies the Hickel rule. So n value 4 plus 2 pi rule.